So thank you. It's a great honor to be speaking at this conference. So we certainly all know about Tate's beautiful mathematics, but something that's being echoed a number of times through this conference is that Tate always loved an example and loved the link between deep mathematics and very concrete classical number theory. Graduate students love deep ideas, but they don't always appreciate how they relate to basic elementary examples. So in my talk, we were encouraged to really speak to the graduate students. I'm going to start off with some remedial class field theory, which is really going to be a background to Milne's talk. Then some hints about p-adic Hodge theory, which will be a background to Bhargav's talk. Then 5 ways to prove the Artin conjecture, and then finally a new theorem. And I've set the standard for what I consider will be a success from this talk. When I gave a talk at Barry's 80th birthday conference, Kai-Wen Lan came up to me afterwards in a very disappointed voice and said, "I really hope to learn something from your talk." I don't think Kai-Wen's here now, but Richard's here, so that will be that's my target non-audience. Okay, so I'd just like to talk a little bit first about class field theory. So the first thing we learn is that a degree P unramified extension of a number field means that the class group has order divisible by P. So let's suppose that our field also contains a pth root of unity. Maybe P is 2. So the following 2 things should be equivalent: the existence of some ideal whose pth power is principal, and some unramified, everywhere unramified cyclic extension of degree P. So what is the relationship between these 2 statements? So since we have a pth root of unity, Kummer theory tells us that all degree P extensions are given by taking pth roots. So it's very natural to look at this and say, well, let's just write down the extension where we take a pth root of alpha. So using the fact that the pth power of A is principal and is alpha, it's not so hard to show that that implies that this extension is unramified at all finite places. Well, dramatic pause, except for those dividing P. And in fact, when you start to look at what's going on at the prime P, things don't seem to work. And there's a few reasons. I mean, first of all, this alpha is only unique up to roots of unity. And if you change the global units, rather, and if you change those global units, the extension certainly can change. But it's even worse. It's not even a question of choosing alpha. There are some number fields where no possible choice of alpha will give you the unramified extension. And you don't have to go very far to find such an extension. I mean, the first example of a number field of class number 2 exactly has this property. Okay, so Kummer theory and class field theory are not really compatible, at least globally. What about locally, where things should be easier? So local class field theory. Well, first, to be a bit more precise, degree P extensions, cyclic degree P extensions, are just given by maps from the Galois group to the cyclic group of order P. This is the absolute Galois group. And so what does local class field theory say? It says there's an Artin map from K star to the abelianization whose image is dense. And in particular, for maps to finite abelian quotients, you can replace the Galois group simply by K star. So the Artin map identifies this group on the left with Homs from K star mod K star to the P to Z mod PZ. And now this does look a lot more like Kummer theory, which is exactly where K star mod K star to the P comes in. So again, still assuming that our local field has a pth root of unity, what does Kummer theory say? Well, we get something similar, but not quite the same. Once we fix the choice, we don't get an identification of this Hom group, but rather of K star mod K star to the P itself to these homomorphisms by Hilbert's theorem 90. It's kind of an explicit map one can write down after you've chosen this root of unity. So even in this situation, Kummer theory and class field theory are not the same thing. So what's going on? So if we take this identification from Kummer theory and this identification from local class field theory, what they really say is that Kummer theory is not just a different way of thinking about class field theory, but Kummer theory gives you some extra structure, namely it gives you the structure of a perfect pairing from k star mod k star to the p to itself. Okay, so if someone came along and said they knew Galois theory, and you wanted to give them the question, I would tell them, can you work out if k is equal to q2 and p is equal to 2, what is this map? I think this is a kind of a great exercise to really understand what's going on. Of course, it's the Hilbert symbol. We can think about it a bit more concretely like this. And this is really the first, kind of the simplest, perhaps, case of Tate local duality. So at least a more general case, well, the most general case, is as follows. I take a modular over gk, I take its dual, twisted by the roots of unity. Then there's a perfect pairing between the cohomology group, even just the first cohomology group for concreteness, between H1km and H1km dual. You can take their cut product and then contract them along the map to mu p, and you get this identification. And this is exactly the maps we just considered before relating class field theory and Kummer theory. And so it might be the case that you think this is just a special case, but in fact, you can more or less prove Tate local duality by some kind of Devassage argument and inflation restriction to exactly this kind of relationship between Kummer theory and class field theory. So let me go back and resolve what's happening globally. So we can also at least get a hint of what's going on there. So again, Kummer theory tells us that degree p extensions are given by adjoining p-th roots. Of course, there are infinitely many such extensions, so let's just look at the extensions with the property that they have some restricted ramification, for example, unramified away from p. Because they're somehow quite easy to understand. I mean, understanding ramification away from p is just about looking at the factorization of alpha and looking at the valuations of primes away from p. So to get such an extension, you really would just want this ideal to be a p-th power, at least if you ignore primes at dividing p. If you change alpha by a p-th power of a principal ideal, nothing much changes. So you really want I to be a p torsion element, not in the class group of k, but the class group of k where you've quotient out by the primes dividing p. Okay, so the construction we had before, what it really tells us is, by Kummer theory, for one of these extensions, well, you can get a p torsion class in this class group, and then the ambiguity of this alpha is units, global units, where maybe we're allowing also units dividing p. Okay, and so here you get yet another way of seeing why this description is different from class field theory. Class field theory doesn't tell you that the p torsion of the class group is related to the extensions. The class group is the Galois group, and so the degree p extensions should be quotients of C. They should be C mod p. Right? And of course, CP is just Pontryagin dual to C mod p. So class field theory, on the other hand, tells us this quotient, well, this captures degree p extensions unramified everywhere. The fact that we've done something at the prime p actually means that these extensions have to be totally split at p. And so when we combine these two together, what we get is we get a count of the extensions that are unramified away from p but split at p, and then the quality between that and the count of extensions that are unramified everywhere at p and totally split at p, modified by some local factor that's easy enough to compute depending on the behavior of the primes above p and the primes above infinity, which of course control the rank of the unit group. Okay. So again, globally, this comparison is now a special case of a global duality theorem. So Tate, of course, really found a wonderful and incredibly useful version of global duality for and local duality for number fields. But in some sense, these were not the first theorems of this kind. I mean, perhaps the first theorem already go back to, another giant of number theory, namely Kummer. If you just take the pth roots of unity, of course, Kummer proved that P divides the plus part of the class group not if and only if, but that would imply that it divides the minus part of the class group. So these versions of these theorems, of course, go back a long way. And so one thing that you get is, of course, a unification and a much more powerful way of putting things together that then becomes very useful for many other applications. At the same time, it's really grounded in something very quite explicit that you can see by hand in cyclotomic fields just by using Kummer theory. Since my talk is about modularity, I'm not going to sort of say necessarily how much it gets used, but exactly this global duality in a particular form proved by Greenberg and Wiles is a completely crucial ingredient. In some sense, it's sort of where most of the content of algebraic number theory comes and goes into the proof of Fermat. Okay, that's remedial class field theory. Now let's talk about remedial p-adic Hodge theory. So let QP bar be the algebraic closure, and let CP be its completion. So the Galois group, the absolute Galois group of QP, or any finite extension, acts on QP bar, but that action is continuous, and so that means it extends to an action of CP. Now there are two, I would say, distinct but very related themes in p-adic Hodge theory. One is to understand the Galois representations that come from geometry, like that come from the Tate module of an abelian variety, that come from the Étale cohomology of a variety. But there's a different theme, which is simply understanding all p-adic Galois representations themselves, and certainly not all of them need come from geometry. So these are really almost surprisingly linked in some sense in the end, but there are two things. And this first kind of remark, these first type of comments are more related to the second theme, and in particular to the work of Sen. So let's suppose we have an n-dimensional representation over QP, then we can form, or let IK be the inertia group, we can form the representation where we tensor over QP with CP. And so just to kind of make sure, that seems like an innocuous thing, you're just extending scalars, but we're doing something quite different. The Galois group is acting on V, but it's also acting on CP in a very complicated way. And that's kind of crucial for understanding what type of thing this is. So one question you could ask is, when do you get an isomorphism of Galois representations with CP to the n? If V was a trivial representation, this would be true. But what Sen proved, and I believe was conjectured by Serre beforehand, was that this is true if and only if the original Galois representation has finite image on the inertia subgroup. So let me also make a remark about the Sen operator, as Bhargav also mentioned. The Sen operator, well, one property that you can say, if it's semi-simple and has integer eigenvalues, then you say V is Hodge-Tate, and you have an isomorphism of VCP with these twists. So of course, the starting point of p-adic Hodge theory was Tate's proof that abelian varieties, well, that the representation of the Tate modules are Hodge-Tate. But it's really kind of the beginning of the story. And so again, in this particular context, the Sen operator is 0, in which case it's certainly semi-simple, and all its eigenvalues are 0, if and only if we have finite image. So I wanted to do another basic example, because the first time you see CP, it's kind of hard to understand, like, where is it coming from? And like, why is it even a natural thing to do? And so I just wanted to do the following example, which I'm sure probably even Serre understood beforehand, which is to show what happens for an unramified representation, but where the image is still infinite. So let's take a two-dimensional representation, and let's suppose Frobenius acts by the following unipotent matrix. So it's certainly unramified, so certainly we expect after we tensor with CP, It should just be CP squared. All right, so well, we can choose a basis. There's a fixed vector v. There's a vector w, which is sent to w plus v. And what is supposed to happen is after we tensor with CP, we need to have a basis with two invariant Galois invariant vectors. Well, one of them is pretty obvious. It's v tensor 1. W tensor 1 doesn't work. You can see that you need to correct it by replacing w tensor 1 by w tensor 1 plus v tensor something. So let's suppose this is the element. Then we want it to be, on the one hand, we want it to be, the inertia group is acting trivially, but we also want Frobenius to be also sending it to itself. And now again here, the key point is that when you take that action, I mean w is sent to w plus v, v is sent to v, but it's also acting on the alpha. So the alpha is sent to sigma alpha. And so you can just read off from here what you want alpha to satisfy. Well, you want it to be invariant under inertia, but you want sigma alpha minus alpha to equal -1. So let's show that there exists such a thing. Let's do it by induction, mod pi to the n. So let's suppose we knew it, mod pi to the n. Start with the bottom layer. We just want to change alpha by something, so it's true mod pi to the n plus 1. So let's just change it by gamma pi to the n gamma. And what do we want gamma to satisfy? Well, we see how much the left-hand side changes. And we only care about this mod pi, so Frobenius is just sending it to the qth power. We want gamma to satisfy gamma to the q minus gamma is beta. And this equation, x to the q minus x is beta. This is a separable polynomial because its derivative is -1, already mod p. So you can see that you can define an unramified extension. Right? We always want inertia to act trivially. We can change alpha by this unramified extension and get it to be closer and closer. But at each step, you're taking a further and further extension. Right? If this element was going to lie in just QP unramified, you would have to lie in a fixed finite extension. But the degree of this extension is at least possibly getting bigger and bigger. And what that means is that this limit element is not actually going to be algebraic. It's going to be in its completion. And you can really check that it won't be algebraic. Well, otherwise, the conjugate of alpha would be alpha plus 1, and alpha plus 2, and alpha plus 3, et cetera. Okay, so even in this most basic example, you really see how CP comes up naturally. Okay, so let me give a few more examples of the theorem, not of any arguments. This will be relevant for what comes later. All right, so let's suppose you have a global representation which locally looks like this on inertia. All right, well, the sen operator will be 0 if and only if it has finite image on inertia. Well, that means only if the star is 0, only if it's unramified. So the sen operator in this type of example can really tell something quite interesting. Another example, here's the following 4-dimensional representation. This kind of looks a little bit like an abelian surface with ordinary reduction. But if it was an abelian surface with ordinary reduction, it should have a quotient, a 2-dimensional quotient that's unramified. But here there's a star. So in this example here, the characteristic polynomial of the sen operator is this, but it's semi-simple. In particular, it's Hodge-Tate if and only if this star is equal to 0, if and only if this representation is actually semi-stable. So actually, for general representations, being Hodge-Tate is a much weaker condition than being de Rham and being semi-stable. But in these somehow very special ordinary situations in various low weights, you can actually get quite a lot of information. Okay. Modularity lifting theorems. So let me say a little bit about modularity lifting theorems. I'm going to restrict to the ordinary case because that's easier to explain and is even relevant for what we do. So let's suppose you wanted to prove all elliptic curves were modular. That's a good thing to prove. The basic strategy is to start with a prime p, to look at a mod p representation, and then by some other mechanism to at least assume that this mod p representation comes from a modular form, and then to prove a modularity lifting theorem, namely that all lifts with appropriate local properties come from a modular form. So for example, in the ordinary case, it's possible to say exactly what you would like to look at, on inertia. You would like it to look. So it has an unramified quotient, and it has an appropriate power of the cyclotomic character. Right? For an elliptic curve, of course, k will be equal to 2, and an ordinary elliptic curve exactly has this description, good ordinary elliptic curve, on its p-adic Tate module. Okay. So again, I'm not going to go into the theory of Galois deformations, but as Barry first understood, these lifts are constrained by the Selma group, this kind of class group with local conditions. And one of the games in the Taylor-Wells method is a delicate interplay between, using global duality, the Selma group and this dual Selma group. You make modifications to one that then modify the other, and this is kind of a key thing. Okay. Now, there's a slightly different way of trying to prove modularity. And this is related to the following. Let's suppose we didn't put any local conditions at P at all. Then you could get many different lifts, in fact, uncountably many. You certainly don't expect them to be modular. But if you put no conditions at all, you do expect them to be modular in a kind of general sense of coming from some p-adic type of modular form. So a different variation on the same thing is first to show that your representation comes from some generalized p-adic modular form, and then to try to argue that this p-adic modular form is actually a classical modular form. All right. The Artin conjecture. So the Artin conjecture says that you have a two-dimensional representation of the Galois group of Q, in fact, any field, but we're talking about Q, then if it's irreducible, its L series should be holomorphic. As Joe mentioned in his last talk, the kind of most interesting case is when the image is projectively A5. And if you want to have any hope of proving this using modular forms, you should assume that complex conjugation has determinant -1. So here are 5 ways to prove that such a representation is modular. Proof number 1 is proof by grad student. This is like a wonderful thesis. I don't know, we heard about in the last talk. Here's another argument. This is by Buzzard-Taylor. So I would say the starting point, I mean, an observation that's kind of crucial at the beginning is that the Taylor-Wiles method doesn't work. So why is that true? So these things should correspond to modular forms, but they're modular forms of weight 1, and they really have quite different behavior to modular forms of weight bigger or equal to 2. And how does that manifest itself in the Taylor-Wiles method? So what do we know about this representation? Of course, it has finite image, so you can replace C by a ring of integers in some number field, and you can reduce mod P. But of course, since it has finite image, this representation is unramified away from some conductor n. So in particular, if you take a prime that's different from n, and you restrict it to inertia, it's unramified. So why have I written as this upper triangular with stars equal to 0? Sort of the problem is that when you try to apply the Taylor-Wiles method, you can't naturally put in the condition that it's unramified, but you can naturally put in the condition that it's upper triangular and it's ordinary. And so what ends up happening if you try to use the Taylor-Wiles method is when you do it, you don't see the fact that star was equal to 0. And so what you produce is, in the end, an ordinary p-adic modular form of weight 1, but you don't know if that's classical or not. Right? There really do exist ordinary p-adic modular forms of weight 1 for which that star is really non-zero and which really don't correspond to Artin representations. Right? So somehow the Taylor-Wiles method isn't seeing this distinction. So at least in some very simplified way, one kind of idea they use is if the Frobenius has distinct eigenvalues, then you can think about it as being upper triangular in 2 different ways, by putting the alpha star 0 beta or the alpha 0 beta star 0. And so by you somehow have to exploit the fact that the star is 0, which the Taylor-Wells method doesn't directly see. So instead, by choosing some ordering, you apply the Taylor-Wells method twice. Then you get 2 different non-classical p-adic modular forms, and then you show that those 2 forms together can only exist if they come from a single classical form. Okay. Proof number 3, Calegari, Winton, Berger. Step 1, prove Serre's conjecture. That's a great way to start proving anything. I recommend it. Now, once you have this, so then you have to use the following observation, which I think Calegari had made previously. So what do you get? Again, you can reduce it mod p. And what does Serre's conjecture say? It says that it comes from some modular form of some weight. But Serre's conjecture only proposes telling you things about things of weight at least 2. And in particular, what you deduce directly is that it's modular of some regular, as in bigger or equal to 2 weight, and that weight is actually p. So that's not so directly related to weight 1 forms. But then there was this beautiful article of Gross, which left out the hardest case, which was then resolved by Coleman and Volok, which is to show that given this weight 1 modular form, weight p modular form, which you also additionally know is unramified at p, you can reduce the weight to this irregular weight 1 modular form. So now we're sort of saying something about weight 1 modular forms. They can be weight 1 modular forms that don't lift to characteristic 0, but you start doing this for more and more p, and you somehow show that the weight 1 modular forms that don't lift only exist for finitely many p, and so eventually you produce weight 1 classical modular forms, which then have to be associated to your original row. Okay. So it's definitely a consequence of Serre's conjecture, but in a non-trivial way. That's proof number 3. All right. Proof number 4. So I told you the starting point of the Buzzard-Taylor method is that the Taylor-Wiles method doesn't work. The starting point of our method is the Taylor-Wiles method does work. And so what the remark is simply that you have to do some modifications to the Taylor-Wiles method to get things off the ground. And then finally, in some sense most relevantly for this talk, is a new argument due to Louet-Pan. So I want to kind of say a little bit about what's going on here. Okay. So again, it's using this argument to say that by some version of the Taylor-Wells method, you show that this Galois representation is modular in some sense of coming from some p-adic object, some p-adic modular form, some type of thing. And explicitly, inside Emerton's completed cohomology group. What is this? Of course, the cohomology of modular curves says a lot about modular forms. If you start looking at the cohomology at higher and higher levels, then you start to have the weights and the levels, mod higher powers of p, start to look the same. And so if you take a limit over all your Shimura, or all your modular curves to infinite level, you can see things of every weight. And so you see it inside this completed cohomology group. Now this is, of course, a limit of cohomology of more and more complicated objects. It's not itself the cohomology of anything, at least directly. And so one thing that was kind of significant was that Schulze gave a meaning, a geometric meaning, to what this tower of modular curves could be. That this limit was some object that you could make sense of in a genuine geometric way. All right, so this kind of completed cohomology is now related to a cohomology of some object, some geometric space, some perfectoid space that you have a handle on. Okay. So now, what are we going to try to do? Now that Mark's here, we can cut to the real content of the talk. Okay. So we have this p-adic modular form, this Galois representation. I mean, it has finite image. And so we know that the sen operator is 0. And somehow, of course, we need to use this. We want to rule out things like 1 star 0, 1. And in fact, that should really distinguish for one of these kind of p-adic weight 1 modular forms, whether it's classical or not. So this sen operator on the Galois side is really telling us whether it should be classical or not. And so the key point here, and this is more kind of in the first framework of p-adic Hodge theory, is that what Louet does is he relates the sen operator, or he gives another interpretation of the sen operator, which is something about the Galois representation, now in a geometric setting of the cohomology of X. Right? In this geometric setting, you can construct a geometric operator which is telling if the form is classical or not. I mean, a type of example that may or may not be familiar with you is, for example, Coleman's classicality result. You have these various maps of things with finite slope, which is determined the classicality. There's not even any finite slope going on here. These are certain locally analytic vectors. But there's a geometric way, a geometric operator in cohomology which is detecting whether the form is classical or not. And so now you have this geometric operator which is detecting if it's classical or not. And on the Galois side, you have the sen operator which is detecting if it has finite image or not. And this Galois representation is occurring inside this cohomology. And so if you can show that this sen operator is equal to this other operator, then you're saying, well, this sen operator is 0, will detect if it's classical or not. Okay, so that's maybe quite reductive, but that's kind of the basic idea. It's you're kind of relating the sen operator to this geometry, and then you're kind of going back and forth. Okay. Yeah, so exactly, you show that the sen operator is 0 if and only if rho is classical. That's kind of what you expect. You may say, well, you're not using its finite image. You're only using the fact that it's finite image on inertia. But of course, from the Fontaine-Mazer conjecture, finite image on inertia should imply that it's finite image as well. Okay, so in fact, Louet even deduces a stronger form of the Fontaine-Mazer conjecture in weight 1 by this mechanism. Of course, even to get off the ground here, you need rho bar is residually modular in order to kind of even find it as a p-adic modular form. Okay. So let me tell you a little bit about proving modularity of abelian varieties of dimension G. So I like to say it breaks up into 4 cases. If G is equal to 0, you have a point, and that case is easy. If G is equal to 1, well then, of course, it's the famous theorem of Breuil-Conrad, Diamond, Taylor, using the Taylor-Wells method. So these are elliptic curves, well, the Jacobians are at least. When G is bigger or equal to 3, it's impossible. And when G is equal to 2, it's a lot like proving the Artin conjecture, but harder. And I mean Artin conjecture, I mean the odd Artin conjecture for n is equal to 2. Right? So why is that? So the reason that the Artin conjecture is hard is exactly because of a difference between modular forms of weight 1 and modular forms of weight bigger than 1. Right? In terms of how you define the formula for a modular form, in terms of coherent cohomology, weight 1 does not look any different from any higher weight. But what is different is when the weight is 2, or bigger or equal to 2, the Eichler-Shimura theorem gives a relationship between those modular forms in terms of functions, in terms of coherent cohomology, with the actual singular cohomology of the modular curves. Right? The classical examples, weight 2 modular forms, you have a differential, f dz is a differential in the upper half plane, and lo and behold, the differential on the modular curve has something to do with the singular cohomology on the modular curve. That's how I feel also. It's a great thing. But when G is equal to 1, cue sad music, you have no such connection. And in fact, that's why modular forms of weight 1 are very hard. They're kind of fickle objects. If you try to compute their dimension by the Riemann-Roch formula, you get a contribution from H0 and H1. They cancel out. You get nothing. And this is exactly the analog of what's happening for abelian surfaces. Now these should be associated to Siegel modular forms of a certain weight. Doesn't even matter what weight it is. But the point is the weight behaves a lot like a weight 1 form behaves. So we're in the same kind of situation. Okay. So we did prove a theorem. We proved that any abelian surface is potentially modular. Okay? And that potential has a technical meaning here. It's not just an ambitious hope. But one consequence of this, or the main consequence, well, maybe I should say that it says that the L function has a meromorphic continuation. But it really stops significantly short of modularity. And to kind of sketch what our proof is, to use one line in terms of these 5 techniques, is to combine the Buzzer-Taylor and the Calegari-Garrity approach. That's the one-sentence summary of our theorem. But I want to talk, in fact, about a new theorem. So let's take an abelian surface. Again, in any kind of Taylor-Wiles type of situation, you have to have some big image assumption. So let's suppose that the mod 3 representation on the 3 torsion points is as big as possible. If you think about abelian surfaces, the ones that don't satisfy this are kind of a thin subset of the moduli space, so this kind of happens 100% of the time. Some more conditions. So I have good ordinary reduction at 3, some condition on the characteristic polynomial at 3, and then some slightly ugly-looking condition at the prime 2. Now, these don't hold all the time, but they kind of hold a positive proportion of the time. They're open conditions. And so these 3 conditions simultaneously hold, depending on how you count, for a positive proportion. And what's the conclusion? The conclusion is that A is not only potentially modular, but is modular. Right, so there exists some appropriate modular form or Siegel modular form such that the L functions agree. So the L function is entire and satisfies exactly the expected functional equation. I mean, here we're just saying it for H1, but you get the expected result for all the other degrees as well. So we are practical. We like to know, is this useful in practice, sort of on the ground, if you meet an abelian surface on the street? So one source of abelian surface is just the Jacobian of a genus 2 curve. If you look at the LMFDB, you'll find 60,000 genus 2 curves. Drew tells me that 60,000 is going to be 60 million soon, so I'm putting in the date. So of those, a few thousand have extra endomorphisms, and their modularity follows from kind of either explicit easy computation or other general theorems. Of the remaining 60,000, 4 of them have been verified to be modular by highly non-trivial computations, by the Buehler technique, in fact, more or less. And so what does our theorem say of the remaining ones? This is just to give you a sense. It applies to this many. So we're batting 186, according to my ratios. And that's more or less kind of right by some reasonable count. Also, just to kind of state the theorem in a slightly more pithy way, I'll give you 2 more versions. One is if you just take y squared is a quintic. This always gives you a genus 2 curve. And let's just suppose simply that it has good ordinary reduction at 2 and 3, and that the mod 3 representation is surjective. Even this you can relax a little bit. Then the Jacobian is modular. All right, well, in fact, being able to write it with f of degree 5, that's actually a very thin condition, right? Degree 5 or degree 6. So let me also give you one where you allow the degree to be 5 or 6. Good ordinary reduction at 2 and 3, big mod 3 image, and let's suppose that X has a Weierstrass point. All right, this doesn't look so much different from the previous theorem, because if you have a Weierstrass point, you can move it to infinity, and then you get a quintic. So here I'm going to do, again, a subtle change, a Weierstrass point over Q2. Then the Jacobian is modular. Okay. So I want to say a bit about how we prove it, but it's always nice to kind of see what the context is, and so let's just remind you a little bit of some of the things Wiles does. So, of course, the starting point, if you want to prove modularity, if you prove a modularity lifting theorem, you also need a residual modularity theorem. So if you take an elliptic curve and you take its mod p representation, how do you ever prove that? Of course, that's Sayre's conjecture, which is very hard. So Wiles uses the coincidence that GL2F3 is a double cover of S4, and then in the context of, as Joe mentioned, using results of Tunnell and Langlands, you can get the residual modularity in this case. And so this allows you to prove that A is modular as long as the mod 3 representation is big. Unfortunately, the mod 3 representation is not always big, and so then he has a second 3-5 trick to instead work at the prime 5. And so here is the idea. First, you remark just by facts of modular curves that when the mod 3 representation is small image, the mod 5 representation has to have big image. So you take this mod 5 representation, and then you try to think of all other elliptic curves which have the same mod 5 representation. They're parameterized by a twist of the modular curve x of 5, which I'll call here a1 of 5. That modular curve is rational, of course, studied by Klein in his book on the icosahedron. And these twists also turn out to be rational, and so that gives you many such choices of points. And by being a bit selective, you can find another point where the mod 5 representation is the same, but now the mod 3 representation is big. So now you show that B is modular by working at 3, and then you deduce that B is modular, and that rho B5 is modular, and then you use modularity lifting at 5 to deduce A is modular. Okay. So a couple of fortuitous coincidences that occur in this game, but it works out very nicely. Okay. All right, so we are looking at abelian surfaces. So when we proved a potential modularity theorem, when you allow yourself to make a change of the base field, proving residual modularity turns out to be very easy. So one of the issues here is how do you prove anything is residually modular? So let's consider the mod 3 representation. Okay, may as well assume it's surjective. So what is this group? Well, if you take the index quotient by the center of the index 2 subgroup, it's a simple group of large order. Right? So it's kind of hard to have access to this in any direct way. So what we're going to do is we're going to move from the prime 3 to the prime 2. So you could take the moduli space of abelian surfaces with level 3 structure, and then you can take this twist where they all have the same mod 3 representation as your original A. It turns out that that's not rational over Q, but kind of very fortuitously, it has a degree 6 cover that is always rational. Right? So it's unirational. So just to give, right, yeah, this is sort of a very large cover. And so what is this degree 6 cover? This original thing is looking at all abelian surfaces with the same mod 3 representation. And more or less, an abelian surface with principal polarization is just a genus 2 curve. And so this degree 6 cover corresponds to choosing a Weierstrass point on that genus 2 curve. So the abelian variety at some theta characteristic. So what does that mean? That means if you have your original A, you can find a different B with the same mod 3 representation. But now you get control over the mod 2 representation. This is now a kind of simpler group. But even better, because of this degree 6 cover, because it has a rational Weierstrass point, it actually has image S5. I say SB, S5, because of course S6 has 2 different conjugacy classes of S5, and you have to be working with the right one. So now S5 is getting towards something of manageability. We have so much choice in B that you can also choose. You can imagine you've even written down y squared as the quintic. You can choose complex conjugation to have some particular form. And so what that means is that the quadratic field inside here is real. And if you restrict your mod 2 representation to this quadratic field, it now has image A5, and it turns out to be the symmetric cube of a representation that's 2-dimensional that has image A5. And our choice of complex conjugation also means that's odd. Okay. So now we somehow linked it to an A5 representation in dimension 2, where we do have the Artin conjecture, now even over totally real fields. And so in this way, you get the modularity. Well, you use the odd Artin conjecture to show that you have an A5 representation as modular. You can move to some regular weight Siegel modular form. You can take the symmetric cube, which exists by Kim Shahidi. That corresponds to a Siegel modular form. And so you get the residual modularity you want now with p is equal to 2. But there are kind of a few things you might worry about, because this modularity is not in the low weight that you actually want. It's in some higher weight. Right? It's coming from the symmetric cube of a regular weight Hilbert modular form, and so its weight is in particular regular. And the theorems that we proved, the modularity lifting theorems, we required modularity lifting, residual modularity not just in any weight, but in that low weight. Right? So you're done. Well, there's a few issues. First, our theorem was for p bigger than 2, not p is equal to 2. But you have to do this way of reducing your form in regular weight to low weight. And you're done, except we don't have such a theorem. We don't know how to prove the analog of these theorems. They definitely rely on the special fact that modular forms have Q expansions, something that, rather the Q expansions are determined by the modular form and by the eigenvalues, and this is something that goes kind of unpleasantly wrong in many other situations. Okay. But at least we somehow reduced it to this horrible simple group of order 20,000, now to things where we know are kind of residually modular, at least in some regular weight. Right, so we reduced it to this B, and we know that it's modular and has image, maybe S5, in some regular weight. Okay. So you can't hope just to kind of prove a modularity lifting theorem directly, but you might hope, just by working in higher weights, to at least prove it comes from some kind of p-adic modular form. All right, to do this, you have to do some kind of slightly unpleasant modularity lifting theorem when p is equal to 2, and the image is slightly kind of awkwardly small. But using some kind of ideas of Jack Thorne, this is possible. But still, you're in this situation of how do you then, in this high weight, how do you kind of show that this thing is classical? So instead, right, our approach in this paper is really quite different from our previous paper. We don't use the Buzzard-Taylor or the Calegari approach. We use the result of Louet pattern. And one reason we can kind of do this is, particularly in this situation, as I showed you, right, even in this case of this four-dimensional representation that's ordinary, you can tell if it looks like it should be classical or not from the sen operator. Right? The sen operator is controlling whether you think the Gower representation is classical. And so, if somehow you can construct, now here on the geometric side, an operator which is the geometric manifestation of that sen operator, and this operator is telling if it's classical or not, then you can do exactly what Louet Pan did and derive classicality. Okay, so a kind of key ingredient here is just the higher Hita theory of Boxer and Palloni. So just a few remarks. If you kind of compare what we did to these previous things, we work harder because, of course, the Siegel varieties have dimension 3, and 3 is bigger than 1. Mighty muscles. But on the other hand, we're also working in the ordinary assumption. I mean, Louet Pan thing applies more generally. And we're also assuming the base is Q. I mean, some things we do for old groups G, some things we do for GSP4 and totally real fields, but some things we do really over Q. And that is kind of makes a few things easier. I would say that, like, it is possible, maybe come back in 7 more years, that there is scope to imagine you could kind of move beyond the ordinary case. Things clearly become more complicated, and also move beyond the Q case to totally real fields. And then you could plausibly hope to kind of remove the kind of a hypothesis that 2 was something to do with the fact that you're forced to work over Q. You try to do some 3-2 trick, right? But if you can somehow work over totally real fields, you can make some solvable extension and then start to get rid of some of these conditions. And so it's not inconceivable to imagine proving a theorem that if the mod 3 representation had big image, then it was modular, and that would apply to 100% of elliptic curves, but you always have this kind of annoying thing. What if the mod 3 and the mod 2 and the mod 5 and the mod 7 representation are all reducible? I mean, I don't even know if there's an abelian surface of general type whose mod 3 and mod 5 representation is bad. Even general, yeah, okay. So, but, okay. Well, we're building it. So I have one more slide. So in this kind of technique, I've kind of mentioned sort of manifestations of 4 of the various ways to prove the Artin conjecture. There's one more. This is the Carré-Winton-Bechet technique. So what about Serre's conjecture? I have no insights there. There's still this issue of going from regular weight to irregular weight, right? If you had that and you had Serre's conjecture, then in fact you could prove the modularity of all abelian surfaces kind of just by how Carré proved it. But this is still a kind of tricky problem. But we do still prove an analog of Carré's theorem, which is the following. So let's suppose you do have Serre's conjecture in regular weight. And again, there's lots of kind of different ways of formulating it. Again, this is for GSP P4 over Q. Even without the kind of gross and Coleman-Volek results, if you have this, then you could deduce that all abelian surfaces are modular. So for example, if someone came along and unsurprisingly found a new way of coming up with non-solvable base change for discrete series for GSP4, then that could give a possible approach to kind of proving this directly. I think that's a good point to stop.